When developing a Mechatronics system, we generally want to use a predictable design. And for that we need a model. This also applies to one of the most commonly used motors, the induction motor or asynchronous motor. But the model of an induction motor often requires parameters that are not in the supplier's datasheet, or a supplier does not make this data available. So how do you figure this out? My name is Stef Wintraak, and in this video I present a practical method based on 3 tests to determine the most relevant motor parameters of a star or Y-connected 3-phase induction motor. To model a 3-phase induction motor I use Simscape. Here you can see an example of such a MathWorks Simscape model. We see a lot of components in which we have the voltage source over here, and the basic parameters of this voltage source, a 3-phase voltage source, is the rated voltage, which is the line voltage. I set it to 400 volt, so it has a phase voltage of 230 volt and the frequency of 50 Hertz. Then we find in this circuit a current measurement device, a 3-phase current measurement device, and here we have the phase permutes, which makes it possible to switch for this asynchronous motor between a Y mode, a star mode, or a delta mode. So putting a 0 over here puts the windings in star or in Y, and putting a 1 over here puts the windings in a delta configuration. And then last but certainly not least, we have that asynchronous machine over here, which is a squirrel cage induction motor. And when you click on it, you see a lot of parameters over here: the rated power, the rated voltage, and the rated electrical frequency. But these parameters are the most difficult parameters to figure out. When we summarize it, we see that it requests the stator resistance, the stator leakage reactance, the referred rotor resistance, the referred rotor leakage reactance, and the magnetizing reactance. So we have to figure out or define a couple of tests to figure out how we can come to a solution for these parameters. So what are we going to do? We are first of all going to set up a one-phase model, and here you can find the one-phase model of an induction motor, which is, from a theoretical point of view, nothing more than a transformer. This is the primary side, which is the stator side for the motor, and here we have the secondary side, which is the rotor for the induction motor. You find the AC source over here, which is connected, of course, to the induction motor. And the induction motor, the stator of the induction motor, is modeled by a resistor, RS, and a reactance, XLS. And the frequency in this loop is frequency F1. And we have a voltage over here, which is transformed to the rotor. E1 is transformed to the rotor side, which is E2. And the rotor is modeled also by a series connections of a rotor resistance and a reactance XLR over here. But the frequency in the rotor is F2, and it's not in all cases equal to F1, because it determines on the amount of slip in the rotor, so in the motor. And we have 2 equations which say that the frequency depends on the slip and that the induced voltage over here depends on the slip. So F2 is equal to S times F1, in which F1 is the mains frequency, and the induced voltage over here is S times E20, which is the induced voltage at locked rotor conditions. So conclusion, when the slip is 0, then we have the theoretical synchronous speed. E2 is 0 volt, and also the frequency in the rotor is 0 Hertz. And in the condition that S is 1, so the slip is 1, so in a locked rotor condition, the induced voltage over here has its maximum value, and F2 equals F1. So that is our one-phase model, but it's difficult to work with. So we need a reduced one-phase model, which is also implemented in that Simscape model. And in this way we connected the rotor to the stator. But to couple the rotor network to the stator, the frequency in this complete network has to be the same frequency. So that's the main frequency F1. So to compensate for the rotor side, we have to divide both the reactance value and resistor value by the slip. And then this yields that we have here the rotor resistance divided by the slip S, and for the reactance we can see that it's equal to omega 2 times L, or 2 times pi times the frequency F2 times L. And in the reduced version, so dividing it by the slip S, we can see that we can substitute F2 by S times F1, and we see that the reduced reactance is equal to 2 times pi times F1, so it's omega 1 times L. So this is omega 1 times FL. And now we have a reduced one-phase model. The thing is that we have to figure out a couple of tests to determine these parameters over here. So what do we want to know? We want to know the resistance value over here, RS, that XLS over here, that's stator leakage reactance. We want to figure out the reduced resistance over here, the reduced rotor leakage reactance over here, and the magnetizing reactance over there. And to figure that out, we're going to do 3 tests. The first is a DC test, then we are going to do a no-load test, and then a locked rotor test. So we start with the DC test. And for the DC test, we measure the resistance between the 2 windings, for instance by using an ohm meter. And when your motor is connected in a Y configuration, that winding resistance, RS, is equal to the measured resistance divided by 2. But probably a better method is that we apply a DC voltage to 2 windings, so in this configuration. And we measure the DC current over there, and then in the same situation we can define RS as UDC divided by IDC, and then divide that result by 2 because of that series connection over there. One remark, be sure that these windings don't heat up, so don't use a too large voltage or a too long measuring time, because a temperature increase in these windings will have a bad influence on the measurement of RS. So that was the DC test. So now we know RS. Now we're going to perform the no-load test. And under no-load conditions, S is very small. That means that this resistance RR over S becomes very large. So this complete model can be reduced by a simpler model, which is the one-phase model under the conditions of the no-load situation. And in this situation we only have the stator resistance, the stator reactance, and we have XM over here. But the complete secondary side can be neglected. So having that reduced model, we can define a test to determine XLS and XM, because this value for RS came out of the DC test. We have 2 methods, and method 1 says, well, let's add the motor to a 3-phase grid. And we measure the line voltage between 2 windings, and based on that we can calculate the phase voltage by dividing the line voltage by the square root of 3. We also measure the line current, and having that we can calculate the total impedance E phase over E line. E phase divided by I line, I should say. We also know that the total impedance of this circuit is equal to RS squared plus the summation of XLS plus XM squared, and then the square root out of that summation. So now we can calculate the summation of these 2 reactances. So XLS plus XM is the square root of Z total squared minus RS squared. During the locked rotor test we will determine XLS, and when we have that XLS we can calculate xm. So after doing the locked rotor test, we can also calculate that xm. Method 2 is almost equal to method 1, but it includes also the measurement for RS, so it's somewhat more accurate because somewhat more losses are included. So what we do in that case, we also measure the total active power, for instance by using an Aaron circuit, because in that way we only need to use 2 wattmeters instead of 3. And we calculate RS by dividing the total active power by 3 times the line current squared. So now we have RS, we have XM, we only need to define these 3 parameters. And we're going to do that by doing a locked rotor test. And in a locked rotor situation, the slip is equal to 1. That means that RR over S becomes RR and will be very small. And so the complete excitation branch can be neglected in this case. So this is our model during the locked rotor test. So we have 2 resistors over here and we have 2 reactances over there. The first method, because we also have 2 methods in this case, is the same as we did for the no-load test. We add the motor to the 3-phase grid, we measure the line voltage between 2 windings and calculate the phase voltage, and we measure the line current. Having that, we also measure the total active power, again for instance by using Aaron circuit, and we can calculate based on that total active power. We can calculate 3 times I line squared times RS plus RR, so that yields RR. Again, we measure the total active power, we measure the line current, we already figured out what RS, what the value is for RS, so we can calculate RR. So we have RS, we have RR, so only the reactances have to be figured out. We can do that by defining that E line over I line is equal to the square root of these resistors squared plus the reactances squared. Well, that yields XLS plus XLR, and we call that in this measurement X locked rotor. Now you have to know that according to NEMA, the induction motors has been classified. We have 4 types of induction motors, class A, B, C, and D. And NEMA says that XLS is equal to 0.5 times the locked rotor reactance, what we figured out by using the equation as I presented before. For motor type B, it's 0.4 times X locked rotor. For motor type C, it's 0.3 times X locked rotor. And for motor type D, it's the same situation as for motor type A. So in that case, we figured out XLS. And because we have XLS, we can calculate XLR. And we can also now calculate XM because we needed that in the procedure of the no-load test. So now we have all parameters, but there is a second method for the locked rotor test, and it's more or less the same. Well, we add the motor to the grid, we measure E line, we calculate the phase voltage, we measure the line current, but we also again measure the total active power. That active power is also defined as the square root of 3 times E line times R line times the cosine of theta. Because we measured the line voltage and the line current, we can calculate theta. And now we can say, well, the locked rotor is equal to the locked rotor resistance is equal to E line over I line times the cosine of theta. And the total reactance in locked rotor conditions is equal to E line over I line times the sine of theta. Well, when we have the locked rotor resistance, and we calculated in a former test, in the DC test, RS, we can now calculate RR, and by having the X locked rotor, which is equal to XLS plus XLR, we can use the NEMA table again for calculating both XLS and then XLR. And of course, we can calculate again xm by using the formula as presented in a no-load procedure. Well, having done that, we now have all the parameters. So now we have a measure presented how to determine or estimate the main parameters for a three-phase induction motor based on three relatively simple tests and some calculations. The method presented is based on a star or Y-connected rotor, but the approach for a delta-connected induction motor is essentially the same. Thank you for watching, and I see you next time. Bye-bye.